Good afternoon, everyone. Welcome to this seminar. Today, we are very happy to have Dr. Chung to give us a talk. He received his bachelor degree from National Taiwan University in 2003 and a PhD degree from Harvard University in 2011 in computer science. After his PhD, he was a postdoc researcher at Cornell University and supported by Steeman Postdoc Fellowship from 2010 to 2012. And he joined the Institute of Information Science, Academic Sinica in 2013, and then became a research fellow in 2020. His research interest lies in the field of cryptography and the interplay with complexity and quantum theory. So let's welcome him.
Hello, can everybody hear me? I guess so. So thanks, Professor Guan, for the invitation and also for the introduction. I will talk about joint work with Jia Naihui and Lai Qingyi. From last year. I will mention the title. But before I start, so let me try to introduce myself a bit. I'm from Academic Sinica, and I'm from Institute of Information Science. So I'm not a physicist, I'm a computer scientist. Because of Professor Guan and many others, I continually have a chance to interact with physics people. So I keep trying to see how well or how should I talk about this so that it can be very well. So today will be another try. If you have any questions, just let me know anytime. And also after talk, if you have any comments or if you find it's very difficult to follow, please come to talk to me, and then I can find a better way to talk about this next time. And I think we have a relatively small audience today, so it will be great if you can really raise your hand and ask questions during the talk. Okay. So given this is a research from computer science perspective, it will be probably very different from what you usually see from other talks in physics. So I will try to not get into too much detail, too much technical detail, but try to talk about high levels and talk about the story, and hopefully at least you will know what's the question we try to answer and how do we answer the question from the computer science perspective. Okay, so the title is on the power of hybrid classical and low-depth quantum computation. We will slowly talk about what it means later. As mentioned, I won't talk about technical detail, but there will be an online version of the talk by Jia Naihui available online. So if after the talk you find the topic interesting and you want to know more about it, you can go to online and then look at the more technical presentation of this work. Okay, so let me get into the story directly. So I would like to talk about the underlying motivation of our work. Also kind of recent news about content supremacy, which serves as a very great motivation for our work. So I think maybe all of you here have seen this breaking news happening last year and a few months ago. So this is the first content supremacy demonstration by Google. And this is the second one demonstrated by Professor Pan Jianwei's group using quantum optics for content supremacy. So I would not get into the detailed story behind it, but let me use it as a motivation and tell you at high level what does it mean by content supremacy, or rather just to remind you about what does it mean by content supremacy. So content supremacy means that we would want to use existing content computer to efficiently solve some classically intractable problems. So it's important that we use content computer we have today, and it's important that we solve some classically intractable problem, because that will mean that today we have a content computer that can, in some aspect, outperform classical computer in some sense. And this is a goal that we have tried to achieve for many decades, and then finally, recently, we have a solid experimental demonstration that we have achieved this goal. And as today, this classically intractable or this hard problem are actually somewhat contrived. They are not problems that we actually want to solve. They are problems we decide to for the purpose of demonstrating content supremacy. But already like this is already a challenging goal, and it's already a great milestone in the development of content computation or content computer to achieve this goal. So I think this should be the quote from Google's Nature paper, that they demonstrate content supremacy using a programmable superconducting content processor. And what they claim to achieve is that they can do some task. I will not get into what task in this talk, but they will find the answer to some task in 3 minutes using their content computer. But they estimate that the best classical supercomputer will need to take 1,000 years to solve. And later on, IBM said that, well, your estimation is not quite right. Maybe we can solve it in a few days. But still, 3 minutes and a few days are still a large gap. So it's still valid to say that what Google has demonstrated is a content supremacy. So a natural question would be, what can near-term content computer do? After we have demonstrated content supremacy for some contrived classical intractable problems, what should be the next goal? And what should we expect? Okay, so let's look closer to what's actually achieved by Google, or what's the power of the near-term content computer. Okay, so what does near-term content computer look like? So if you have looked at the kind of popular science description of content computer a little bit, right now when we talk about programmable content computer, we almost always talk about the computation in the content circuit model. But it just means that we will have a few qubits, initialized as some zero state, and then we can operate on this qubit using some quantum gates, like Hadamard gates, X gates, CNOT gate, etc. And this gate will carry through certain computation and then bring the input quantum state to some output quantum state. And then we will perform some measurement, and then we'll get some classical result. And this classical result will be the computational outcome of this quantum circuit. And this is analogous to the classical circuit model, where we have some classical input, and we do some classical computation like AND gate, OR gate, or NAND gate, and then at the end we have some output. Okay, so this is how we want to think about content computation in the near term. So what can Google do with this model? So, or what can maybe we do as the whole world in maybe the next 3 to 5 years? So Google has 53 qubits. So in near term, likely we could have gone beyond 100 qubits soon. That just means that here we will start with more than 100 qubits to compute on. And then we will do some gate computation, but currently and also necessarily, those gate operation will introduce some noise. And at the moment, the noise is quite large and will accumulate fast. And what the effect of it is that we will have to be restricted to quantum circuit with small depths. By small depths, I just mean that, okay, here, for these qubits, we can only operate on it for a small number of layers. And specifically in quantum's experiment, in Google's experiment, Google can only do this computation for only 20 layers. And the reason is that the fidelity is roughly like 0.2%. After accumulating the noise for 20 layers, it's already very noisy and it's already actually very difficult to get the output from the computation because it will be kind of colluded by a lot of noise. So this is what near-term quantum computer would look like. It would have not too many qubits, and more importantly, it will have a very small quantum circuit depth until we can make the fidelity much, much better. But what should be a theoretically ideal model for quantum computation? Ideally, we would like a quantum computer, like a classical computer, where we have gigabytes of memory, terabytes of hard disk. So we want it also have many, many qubits. We also, of course, we need the error to be small so that we don't have a restriction on the quantum depth of the computation. And we want, so once we have a sufficient small noise, ideally we can perform arbitrary computation on it. In particular, we should be able to do polynomial number of steps on our quantum circuit and with polynomial number of depths. So there is no restriction on the number of layers and no restriction on the number of operations we can perform on the quantum computer. That would be an ideal scalable quantum computer. So apparently there's a gap. So let's imagine that this orange box to be all the computation problem that we can solve using a polynomial depth general quantum computer. And we know, or very likely, we know that this quantum computer will be more powerful than classical computer. So this blue circle will be the problem that can be solved by the classical computer. And there is, of course, a gap between the two. Now we have this near-term small depth quantum computer. It has, of course, relatively limited power than the general computer. And it could have incomparable power than to the classical computer. And so let's just draw a kind of green circle to denote the problems that we can solve using small depth quantum circuit. So a natural question is, how do we use the power of small depth quantum circuit? So now we have what we available for a green circle and also what we available for a blue circle. So a natural idea would be to try to combine the two. So a natural idea is to combine small depth quantum circuit together with the classical circuit. And here is a kind of intuitive way how you can combine very naturally. So we have a small depth quantum computer. We can use it to do some computation and get some classical result. Now we have a classical computer that can do additional classical computation to post-process on the result. And after that, we can maybe decide to ask the small depth quantum computer to do another computation. And this small depth quantum computer will again return some classical result for the classical computer to process. And this can continue for many rounds. So this certainly would be at least as powerful as small depth quantum circuit, quantum computer itself, as well as at least as powerful as classical computer itself. But intuitively, by combining the two, we should get something more powerful. So we can get this maybe pink circle that's bigger, that would represent the computational problems that can be solved by this small depth quantum computer plus classical computer hybrid computation model. Okay. And indeed, there are evidence that this pink circle will be more powerful. So for example, Shor's factoring algorithm can be solved in this model. But we do not know how to run Shor's algorithm using only small depth condenser computer. We need to combine it with a classical computer. There are also maybe some heuristic quantum algorithm like VQE would naturally fall into this category. So this is an interesting computation model. We would like to understand its power. So the main question of our work is try to understand the power of small depth quantum circuit together with a classical computer. You can think of it, a computation like this. Is this computation model as powerful as general quantum computer? Or is it still weaker and we still need to get our head, make significant effort to increase the depth of our quantum computation? So is the question that we want to ask, we want to solve in this work clear? Or is there any question that I can clarify?
So that the general quantum computer is not error correction implemented.
So this is just ideal code, so let's assume it's error corrected, so no restriction. As good as you can imagine. Yeah. Okay, so
but does that mean you have a polynomial n depth?
So okay, I actually will talk about it fully here in the next two slides. But the short answer to this is that this n just means the input size. So it's the number of qubits we can operate on. And we usually say polynomial time is an efficient time we can actually do. I mean, we cannot do exponential time computation that's taking too much time. So that by poly n just means all possible efficient computation. Okay, so related to Susan's question, the first question I want to talk about is actually how to formalize such question. Because this is a question we ask from computer science aspect, and there are certain ways that we would need to formulate it in order to be able to answer this question theoretically. So the first question I need to tell you is how to formalize this question. And for this, I need to tell you a little bit of the basic concept about algorithms and the complexity in order to kind of tell you how to formalize the question. Okay, so when like in the past 10 minutes, I keep talking about computation problem, and I talk about these circles and these boxes represent the computation problem that we can solve using this kind of computer, that kind of computer. But what do we really mean by this? So by computation problem, it's just it's easier to describe by example. So the problem is something like, okay, I give you a sequence, ask you to find the largest number in the sequence. So this is a computation problem. The task is to find the largest number. Or I give you a sequence, ask you to sort it in descending order or increasing order. This is another problem. Or I give you two numbers and ask you to compute the multiplication of the two numbers. So computation problems are certain computation tasks that's defined by its input and output. So for this simple example, the input will be a sequence of numbers, and the output will be the largest number in the sequence. So this is a computation problem. And the algorithm will be some well-defined procedure to find an output given the input. For this simple one, the algorithm can just simply read through the sequence and then find the largest one. So read and compare the numbers one by one. And we would like to evaluate or measure the complexity of the algorithm. So it means the number of steps or the running time for an algorithm to solve the problem. So for example here, we have 5 numbers. In general, we can have n numbers. So given n numbers, what's the number of steps we need to do in order to find the largest number? And for this example, it should be pretty simple that this this computational question can be solved in linear time. In time, linear to the number of input. Just by comparing and read through it, so it should be ordered. Okay. And in general, this is the way kind of we evaluate the complexity of computation problem by the running time that an algorithm needed to solve it. Of course, running time can depend on maybe we use classical algorithm or we use quantum algorithm that can have very different running time. But in general, that's how we evaluate a computation problem. And in particular, we evaluate running time in terms of its input size. And we say that an algorithm is efficient if its running time is polynomial in its input size. For example, the algorithm to find the largest number would take order n time, which is efficient. But an algorithm that, say, doing factoring would take something much bigger than polynomial time, like explanation time. Okay. So this, and just to give you more example, the multiplication example I mentioned, the input for this computation problem would be two numbers of n digit, like two 4-digit number are equal to 4. And the output would be the number which is the product of the two numbers. And if we remember from our elementary school, the textbook multiplication algorithm will require to multiply each digit of the two numbers in pair. So in total, we will need to do order n squared number of operations. So the running time will be n squared. And let's look at another much harder problem, factoring. The input is kind of an converse of multiplication. The input will be n-digit number, say this number, and the output will be a factors, non-trivial factors of this number, capital N. And if you think about what we learned from the school, you will find that it's not like multiplication that we learn a simple algorithm we can calculate by hand. In the school, we never learn how to do factoring. And the reason is that we actually don't know how to do factoring efficiently. The best known classical algorithm will require to take this weird running time to solve the problem. But suppose we have quantum power, we can run Shor's algorithm, then we are able to solve this problem using quantum algorithm and using only n-cubed steps. And here you can think of n-cubed steps as just n-cubed number of gates in the quantum circuit. Okay, so here I was kind of imprecise about what we mean by running time, because like in a computer, maybe a running time is one CPU instruction, etc. But for today's talk, we will talk about circuit model. So in a circuit model, the running time would simply be the size of the circuit, and which simply means the number of gates. And we talked about depth already. So the depth will be the number of layers in the circuit, which also means the number of kind of sequential steps we need to perform computation on this quantum circuit. Okay, so far any question about the kind of computational problem, complexity, algorithm, this basic concept? Okay, so if it's fine, then let's go back to our question. So again, our question is to compare the computation power of small depth quantum circuit plus classical computer versus general quantum computer. Yeah, so this is the same picture. Just to remind you again, by this hybrid computation, we can think of it pictorially this way. We perform some small depth quantum computation, and then do some classical computation on the outcome of the quantum computation, and then launch another small depth quantum computation, and then do another classical computation, etc. And how does this compare to general polynomial size, polynomial depth quantum computation? So we need to be a little bit formal. We need to quantify what do we mean by small depths. A convenient theoretical quantification would be just to say it's a log n depth. Because log n would be scale exponentially smaller than its input size. So when n grows, this log n will be much, much smaller than n. So this will model a small depth quantum computation nicely. So a bit more formally, we can ask the question this way. Can all computation problem P solved by polynomial depth quantum circuit, like factoring, can be solved in n cube time, be solved by log n depth quantum computer together with a classical computer, combined in this way?
Is there anything between log and n?
Of course, right? Log square n, square root of n. So you can ask the question in more like fine-grained way and then parameterize the depth as a function b of n of the input. But for convenience, let's just talk about log n versus poly. Yeah. Okay. Okay, so more pictorially, are this inner circle and the outer circle actually overlap, actually equivalent? Or this inner circle is really smaller than the outer circle? And by this really smaller, it means that is there any computation problem that lies in this outer circle but not lie in the inner circle? So again, if we want to show that they are not equivalent, we need to find such a problem here. If we want to show that they are equivalent, then we need to show that every problem here has an algorithm of this complexity.
So the log n depth is including the process you input the data to a system.
That's a good question. So it's tricky because log n depth is small, right?
Yes.
So to make it more concrete, you can think of it this way. So you can think of the input already encode your, the initial state of your quantum input already encode your input. So for example, if you want to factor a number n, this n is written in the initial status of the quantum register. Of the quantum.
So the log n depth is only including the process you process encoding quantum state.
Yeah, so the number of layers. So this layer is log n layer. Yeah. But the number of qubits is many. Yeah. Okay. Good question. Yeah, that will help me to clarify concept. So if you have any question, please ask like this. Okay. So what do we know about this question before our work? And it's kind of an interesting situation. So on the positive side, we know this Shor's algorithm that I already talked about can be actually implemented with log n depth quantum circuit together with classical computer. And it also means that this hybrid model is already sufficient to break certain crypto systems used today. And also there is a positive conjecture about it. So Richard Joseph has conjectured about 15 years ago that maybe any polynomial time quantum algorithm can be implemented with only order log n quantum depths interspersed with polynomial time classical computation. So this quotation precisely means this sentence here, and we should already be kind of familiar with this kind of statement. So any problem can be solved by general quantum computer, can also be solved by small depth quantum computer together with classical computer. But on the other hand, there will also be a negative conjecture in the literature. So Scott Everson in around the same time have an opposite conjecture that polynomial depth or general quantum computer is strictly more powerful than this hybrid computation model. And there's this technical term, this oracle problem. I will explain maybe in a few slides. But for now, just ignore this technical jargon. Just think of it as a computation problem. And I will tell you why we need to consider oracle problem later. So, given the status, our result is kind of answers to these conjectures. So what we show is that indeed Scott is right, and Josa is probably too optimistic. So we show that there is indeed a computation problem we can define, and we can show that this problem belongs to this outer circle, but does not belong to the inner circle. But this problem is an oracle problem. And again, this just means that this problem can be solved by a polynomial depth quantum computer, general quantum computer. But if we are restricted to using logarithmic depth quantum computer together with the Casio computer, we still cannot solve this problem efficiently. And by cannot solve this problem efficiently, we mean that this problem cannot be solved in polynomial number of steps. Okay. And since this is a conjecture for a while, so some people in our community and the trials actually tweeted about this result. And also there's an independent work that answers this question, actually prove almost the same theorem using a different oracle problem. So it's like we find this red dot here, and they find another dot here. Okay. And this is more like repeating what I said. And let me just say it to make sure everybody understands. So how to show such a result? To show such a result, we need to define a computation problem such that this problem can be solved by polynomial depth general quantum computer. That means it lies in the circle here. But this problem cannot be solved by low band depth quantum computer together with classical computer. And to do so, we need to design a problem that's not too hard, and this is by design. It's usually easy to do. And the difficult part is to show that the problem is hard, cannot be solved in this hybrid model. And actually, showing a problem is hard itself is extremely difficult. And actually, we don't know how to do it. For example, you may have heard of this P versus NP problem, whether the complexity class P and the complexity class NP are equal or not. To show P not equal to NP, we need to show that some problem is in P that cannot, some problem inside NP that cannot be solved by polynomial time algorithm. And we are very, very far from being able to prove it. And actually, we are even far from proving like a computation problem requires superlinear time. Again, we cannot do the following. Given that we want to design a computation problem. This computation problem, we want to show that it's hard in the sense that there is no n-squared algorithm to solve it. N-squared time algorithm to solve it. We want to show there is no such algorithm there is no n-squared time algorithm to solve certain problem. For any problem, we cannot prove this thing. And we actually have some barrier results saying that we cannot prove it. Mathematically, we are not ready to prove it. So that's why we did this oracle problem. So we don't know how to prove a problem is hard, but we know how to prove that an Oracle problem is hard. I still haven't told you what do I mean by Oracle problem, but just emphasize on the story. We can prove hardness of Oracle problem, but not hardness of any conventional problem without Oracle. That's why we need to work with the Oracle problem. Okay, so finally, what is an Oracle problem? And this starts to get technical, so I will actually not kind of discuss this too much. But if you have if you have taken classes in quantum computation, you probably remember Simon's problem, you probably remember Dolce-Josa. Those are Oracle problems. And probably you still don't remember why they are Oracle problem and what Oracle problem mean. Even if you may have vague memory about Simon's problem. So let me try to refresh your memory, your memory. But if you haven't heard about this at all, then I'm not sure how useful what I'm saying here. And you can let me know if my explanation makes sense or not afterwards. Okay, so let me see. Okay, so first of all, I should tell you what do I mean by an oracle. So an oracle would just be some function in a black box. And so this is, we will call it F oracle. And this function our computer or our algorithm can make query to it. So the algorithm can ask this black box oracle some input X, and this oracle will tell the algorithm f of X. So this oracle encodes some function, and you can query to learn the value of the function. And an oracle problem would be a problem that's defined with respect to an oracle. So for example, this Simon's problem here, the oracle would be some function mapping n bit to n bit. And this function will have some special form that there is some hidden shift s, such that f of x equal to f of y if x and y differ by this shift s. So for any x and y such that x equal to y plus s, this plus is bitwise XOR. The function value are the same. But for any other pairs of x and y, f of x will not equal to f of y. So in a sense, you can view this function f as a very complicated way to encode this hidden shift. And the seventh problem would be giving you an oracle and ask you to find this hidden shift. So this is an oracle problem. And if it's a classical computation, maybe it's easy to imagine. So I'm a computer, there's a box, I do some computation, I ask x to the box, and then the box or the oracle give me f of x, and then I do some more computation, and then I ask another question, etc. And by asking many, many questions, I would like to learn s. In the quantum case, it's a bit trickier. We need to define what we mean by query this oracle in a quantum way. For example, we can have input be in a superposition, and then we will learn the output also in superposition. And there are some technical details about what it means, which I will not get into now. But hopefully this gives you some sense about an oracle problem. Yeah, this is continuing to describe that what do we mean by oracle access, quantum access to an oracle. So the details I will not get into, but maybe an important note here is this. So if our quantum computer only has a small depth, like a depth d, only D layers, then this content computer can also only make at the most D sequential queries to the oracle. And this is the main restriction for the content or low depth content circuit to solve this oracle problem. Okay, so again, now we are in the oracle world, so we can try to find a computational an oracle problem P. This will mean that we can find what is meant by, find this computation problem we like, and also the oracle. The problem and the oracle are defined together, and we need to find this oracle problem that's easy for poly-depth content circuit, but hard for this hybrid computation. And the rest, maybe 5 to 10 slides, will be to describe how do we find the problem, how we define the problem. But I think I would rather to just skip this part, because probably you will not get learn too much from such a technical discussion. But the slides are there, and after talk, if you are kind of really curious about it and want to get a sense about what the oracle problem is, feel free to come to talk to me, and then we can go over the slides, and I can tell you more about the idea behind this oracle problem. But yeah, so in one word, we will start from Simon's problem, and then we will try to do some complicated thing to make it slightly harder, in the sense that it still can be solved by, for example, depth content computation, but it becomes harder for this hybrid computation model. Okay, so I think the take-home message is maybe kind of the meta level, like what's the high-level question we ask, and how do we formulate the problem in kind of a computer science or theoretical computer science way, and how do we approach the problem. And the main conclusion is that indeed these two are separated, and maybe also answer Sun-Sun's question. Indeed, they are more refined way to kind of parameterize this low-depth content circuit, and which actually show a much sharper separation that even for D versus 2D, there is already a separation. And this proves Anderson's conjecture, but this does not fully disprove Josat's conjecture, because we talk about oracle problems in this relativized world, but that's also the best we can do. And so I still have maybe 10 to 15 minutes. I kind of decide to maybe talk about some more things that I recently prepared for other venue, but maybe it's interesting to talk about it for business audience. And I'll just do it and let's see how it goes. So this is what I want to talk about, is that okay, there are lots of going on in the development of quantum computation, but what should we expect about maybe in the near future, what will be the application of quantum computation? Maybe from a theoretical computer science perspective, or maybe to be more conservative, maybe from my personal perspective. And the way I would like to kind of discuss this question is to first do some classification and also compare quantum computation with classical computation at the same time. I think that would help us to put things into context and to see more clearly what should we expect. So I have quantum computation and classical computation, and here I have provable algorithm and heuristic algorithm. I will talk about what they mean later. But just to give you some examples, for each of the category, there are many algorithms. And let me just talk about it one by one, and then come back for conclusion. So first, let's start from something we know, the classical provable algorithm. And just by example, if we take algorithm course in computer science department, we will learn how to do sorting algorithm, we will do how to do multiplication algorithm, and graph algorithm like shortest path, spanning tree, and maybe hash algorithm or other data structure algorithm, or linear program, etc. All these algorithms are provable in the sense that the algorithm's correctness and efficiency can be proved theoretically. I can construct a sorting algorithm. I can tell you my sorting algorithm will always output a sorted list, and my algorithm will run in time n squared over n log n. And another example, the test of multiplication, we know that it will give you the right answer for multiplication, and it will take time n squared. And there's a much smarter multiplication algorithm called the best Fourier principle. If you take some algorithm or advanced algorithm course, you will learn this multiplication algorithm, and that can do multiplication in n times log n step, much faster than n squared. If you want a number, if you want to multiply two numbers with 1,000 digit, n squared is million, n log n is 10,000. So provable algorithms are very nice because we don't need to test it. If we can prove its performance, we can just implement it and use it, and we will know for sure it will work. And it can be also very practical and used widely, like this FFT is widely used algorithm, in particular in maybe communication, graphics, or crypto. That's extremely useful. But that can also be extremely inefficient even if it's provable, but it's theoretically interesting or theoretically important. And just to give you examples, if you are given a number and you want to know whether it's a prime, there is a smart primality testing algorithm invented in early 2000 that runs in time n to the 6th deterministically. I mean, actually, initially it's n to the 12th, and then it's improved to n to the 6th. If it's n to the 6th and the input n equal to 100 or 1,000, there's no hope you can run it in your computer. And also, there's a very smart matrix multiplication algorithm. Okay, here we are multiplying to n by n a matrix. So the stupid way would be taking n cubed time. Just multiply all the elements in the usual by definition. But there's a very smart algorithm that runs in time n to the 3, 2.37, blah, blah, blah. And this is the result in the last year. That improved the previous result by maybe the 4th digit or something. Okay. Okay, it's very good. But this big O notation hidden extremely large constant. So for this algorithm to be outperform n cubed algorithm, the n need to be maybe 10 to the 10 or even larger. Okay, so this is just proof of algorithm. Now let's move to quantum proof of algorithm. How do we know? Okay, examples. It's good for us to get some sense about what we are talking about. So those are famous Schwartz algorithm, Grover search, Hamiltonian simulation, HHL, etc. Again, they are provable in the sense that the algorithm's correctness and efficiency can be proved theoretically. And that's very nice for quantum because it means that the research or the design of the algorithm does not require actual quantum computing. We can do quantum algorithm research before we build quantum computer for provable algorithms. And indeed, we already studied this subject for decades, starting from Shor's algorithm and Grover's algorithm in the 90s. However, the issue is that while we already achieved this important milestone of quantum supremacy, near-term quantum computer is still too small to run these algorithms on meaningful size of other instance. We only have roughly 100 qubits now, so we cannot hope to solve factoring for 1,000-digit numbers. And also we have a very limited quantum depth, and we kind of see this is a restriction even theoretically. Okay, so I think the point I want to make is that quantum provable algorithms are algorithms we already studied for decades. We have a lot of nice results, but the quantum computers today are too small for those algorithms. Okay. Now let's move to classical heuristic algorithms, again by examples. So what do I mean by classical heuristic algorithms? Good examples are machine learning, like deep learning algorithm. Probably everybody knows deep learning, even if you are not computer science students. And there's this genetic algorithm, and set solver, simulation annealing, content inspired algorithm, etc. Those are classical heuristic algorithms. So what do I mean? By heuristic, okay, this is my own kind of definition. It's not a standard textbook terminology, but by classical heuristic algorithm here, I just mean algorithms whose correctness or efficiency cannot be analyzed theoretically. And I think deep learning is a great example. Okay? We know deep learning has amazing applications, AI is everywhere, but really theoretically we cannot say, okay, this deep learning will solve vision problems in n squared time with 99% accuracy. That's not something we can prove at all. That's something we can experimentally test, but we cannot prove. So I think an important aspect of heuristic algorithm is that because it cannot be analyzed theoretically, it will require experimental tests to know its performance. So we need to test the algorithm on the instance we care, practical instance or data set for machine learning problems. And then we will know whether it's good or not. So not having theoretical guarantee sounds not so good, but they are still extremely powerful in practice, like deep learning and also set solver. I will not get into set solver here, but I'll just use this as an example. You can ask me offline if you want to know how it is. And both of them have very impressive experimental performance. But for genetic algorithm or simulation annealing, I mean, as far as I know, they have maybe rather limited success in practice. Maybe only for specific domain there are some evidence that maybe it will, but maybe because I don't know. Okay, so this leads to a good comparison to the final part, the quantum heuristic algorithm. So again, examples. Most of adiabatic computation algorithms and quantum annealing, victory, and etc., they are heuristic algorithms. Again, just because their performance cannot be analyzed theoretically. There are some adiabatic computation that you can analyze it theoretically and give some provable guarantee, but they are rare cases. There are more cases than given a problem, we can write an arithmetic computation algorithm for it, but we have no idea whether it works or not without experiment. So again, heuristic means we cannot analyze it theoretically, so research requires experimental tests on practical instance and data set. But however, I think this is like the provable ones, the current quantum computers are still too small to test these algorithms on large instances. Nevertheless, this is still a very active and promising area with lots of proof of concept experiment and demonstration. And if I want to bet, I will bet the first real-world application of quantum computation will come from heuristic algorithms instead of provable algorithms. But I think to set our expectation right, I think we need to maybe aware of the fact that this kind of heuristic algorithm requires experimental demonstration on sufficiently large instances, which we cannot do today. So we don't have very solid ground or evidence that this will work in the future yet. And personally, I'm more conservative on the expectation because what we are now is that it's even highly non-trivial to demonstrate experimentally solid quantum supremacy on contrived classical intractable problems. So I would say that for many applications that maybe we can heard of the claims or applications in the popular press or report are maybe too optimistic in the sense that if we have solid experimental demonstration for those applications, then there's no point to do Google or to do exam, right? Okay, so finally, my personal outlook. I would think that, all of us would like to see quantum computation come true as soon as possible. And my personal take for two important milestones would be demonstration of quantum arithmetic code, meaning construct one logic qubit and make it alive for a long time. And first quantum supremacy for real-world practical testing. And I think intuitive definition for real-world practical test would be the following: test that worth some value, make money, and unsolvable classically. I don't know how far we are from it, but that would be an important milestone for sure. My personal bet would be for two, there will probably be some heuristic algorithm in quantum chemistry domain. And I think it would be very, very unlikely for tests that would require to use large classical data. For example, if you want to use quantum machine learning for some classical problem that would have large classical input training data sets, you would also need a correspondingly large quantum computer in order to actually load the data reliably and do computation on it. But for quantum chemistry, on the other hand, those are problems that can be described just by equations. It's very small description, and it's quantum in nature. So for applications of quantum computer that would come in the near future, I would say that should come from quantum chemistry. And I think here I have maybe different opinion from Susan. Probably I think one limit will be happening for two. I think the other day I heard from Susan using two is very difficult. So I'll put it here for potential discussion. I'll end my talk here. Yeah.
question or comments?
No. After this talk, I'm going back to attendance now to tell President Liao that you came here to slap on our face. Well, anyway, serious question. Okay,
yeah.
So from your previous slides, you actually don't believe that D-Wave is working.
I think it's still in an ongoing debate, right?
Well, did you see any work from them? Any meaningful work from them?
Yeah, I guess there are different standards, right? So, for example, for this content supremacy, it will become a breaking news. Then I don't need to search for Google. I just browse my Facebook, and then everybody knows this news. And for D-Wave, I don't see this news on my Facebook. So, I don't know. We need to wait.
Any other questions?
But let me emphasize that I want to be positive. I mean, I think we all want to see applications. It's just that I think we should think more carefully about the right expectations for applications. That's the point I want to say.
Any more? Okay, maybe ask a question. You mentioned earlier in the paper that they discussed we can do factoring using the NISQ machine plus classical computer. So, do you know, do they have an estimate for example, factoring, okay, 2000 bits integer? What would be the resource they need?
For this specific work, is still a theoretical work, and they try to optimize in terms of the depth, so the size will actually grow up. So if you want to find the factoring algorithm that uses a small number of qubits as possible, this is not the one you want to consider. And there are indeed a few careful works from crypto community that do very careful optimization and estimation about the number of qubits needed to factor, say, RSA 2048.
Yeah.
And that will be probably just 2 or 3 times 2048 qubits, logic qubits.
So this is a large quantum computer with small depth.
Yeah, there's always trade-off. If you want to optimize for depth, you need to pay in size.
But I thought you need error correction implemented quantum computer to solve this large number.
Yeah. So I said you need this number of logic qubits.
Yeah.
So
this means your standard is a log n depth QC plus classical computer can solve. So is this statement true or?
No steps and many logic qubits. or maybe if we have. Okay, so for this one, I think this log depth will still have a large constant inside. So
okay.
So you still need error correction. I think, yeah.
Right. Any other questions? If not, let's send the speaker. And we have a tea time now, so.